Among our remarkable resource personals, we have with us Ms. Mahima Mary Mathews. Ms. Mathews is an accomplished academic and holds a BTech degree in computer science and engineering and an MTech degree specializing in data science. Both degrees were obtained with first-rank honors from the Cochin University of Science and Technology in Kerala, India. Currently, she is pursuing her PhD at IIIT Kottayam and serves as the research coordinator and consultant at CyberLabs IIIT Kottayam, while engaging in multiple industry projects within the field of cybersecurity. Ms. Mathews' research interests encompass various areas, including post-quantum cryptography, quantum communication, and many more. She holds the position of principal investigator for quantum computing research projects supported by the IonQ Research Credits Program. Her contributions to the field are notable as she has published numerous papers and received accolades such as Best Paper Awards for her work. I now request Ms. Mahima to take the floor and upskill us on the topic quantum cryptography.
Am I audible? Yes. Okay. So hope you have got the document important links, and hope you have created the account in IBM Quantum, because we will be going through, sorry, we will be going through like the platform for few demos. Okay. So firstly, who was new to this area, like quantum technologies, and or like, please raise your hands so that I can understand the audience I'm like dealing with. Who has like come across some videos or something related to quantum, or at least tried the IBM quantum experience? Anybody? Just one person. Okay. 2. Okay. 3. So I understand that like I have a set of people which is getting introduced to quantum. So I will try to maintain that. Make sure you get some takeaway. Okay. So when we talk about cryptography, it's important to start with the basics. So I'm pretty sure there are many people who are new to cryptography area as well. So so I thought I'll start from there. So obviously cryptography is coming under a broader area called cryptology, and which is actually dealing with creating and solving codes. And it mainly focuses on securing some information and obviously trying to break them as well. So the securing part is actually called cryptography, and you try to break the systems, that is called cryptanalysis. Okay. Now, it's always a tendency to think that when we talk about security, it's always revolving around the data security. So I want to bring your attention to the focus that it's not about securing this data alone. Suppose you have a server, okay, which is handling very important and critical information. Now, to secure that data, is an encryption system or certain algorithms alone enough? No, right? We need physical security in place, like who can access the server room? Who are the people who can like change the configurations in the server? What is the hosting, like who can access certain things and all? So that's what I want to emphasize on this. When we talk about security, it's actually a collection of securing things at these 5 levels. Like you have to secure the hardware that is involved, the software, the network. The people should be educated to use it properly so you can implement the best security systems in the world. And if the people going to use it is not aware of the right way to use it, then you cannot have a good security system in place, right? You cannot reap the benefits of the security system you have implemented. So procedures and data. So what I want to emphasis here is that security doesn't this is not only about data security or like the encryption or certain algorithms alone. The whole package needs to be built properly. Okay. Now, I want to introduce classical cryptography before jumping into quantum cryptography. So why we need, and I would like to introduce, I would like to introduce what are the areas where quantum cryptography can provide a better impact in the current scenario. Okay. So classical cryptography, when it comes to, as I told, like it's the algorithm. So there are certain procedures and algorithms related to the software or the procedures or things that is implemented. So in order to achieve confidentiality, so I'm just using the terms, confidentiality means only the intended person can read it. Okay. So for that, we make use of encryption schemes. Okay. Now for ensuring that the data is not modified or the origin is assured, like I am sending something to a person, that person has to assure that it is from me. Okay. So that's where we need certain concepts like origin integrity, like we assure using digital signatures and all those concepts. Then we also have asymmetric crypto systems, which again provide sort of encryption, but they support key exchanges today. So I would like to take you through these schemes. So when it comes to classical cryptography, I'm starting with encryption. So understand that we have encryption schemes, we have integrity assurance schemes, we have authentication schemes. There are n number of schemes. Okay, it can be built using these algorithms. Okay, clear? That's how we build these systems. Now, when it comes to classical crypto systems, the fundamental, it comes down to having hash algorithms, symmetric schemes, and asymmetric schemes. Okay, so I have like to the people who are very new to this, it's for them. Like when we have symmetric encryption, it means that you are going to use single key for both encryption and decryption. Okay. And for asymmetric, you have a mathematical component behind that. It works in pairs. And if you actually encrypt using a certain person's public key, you actually decrypt using that person's private key. Okay. So I'll like take you through that. So this is CSE-Cyber example. So here you can see that it's actually a simplest symmetric cipher where you have a shift of 3. Okay, so for A, B, C, it goes with D, E, F. So suppose my data is BAT, okay, B-A-T. So I will write it as B will be replaced with E, A will be replaced with D, and T will be replaced correspondingly. Okay, so that is symmetric, simplest symmetric, where you have a key. What is the key there? It is the shift, right? Anybody who knows the shift, they can come back and understand that it is BAT, right? Clear? This is a simplest symmetric scheme. Now, when it comes to like the ones that we use in practice, it's actually like advanced AES, advanced encryption standard. So I wanted you to understand the complexity of these algorithms. That's why I have this diagram over here. So these are mostly based on like certain operations. Okay, it's not based on mathematical principles. So you do certain operations like shifting, mixed columns, XOR, like that, certain operations, like you can read there, like add round key, certain operations are there. And based on these operations, you combine it with a secret key and finally you get a ciphertext. Okay, like you convert it into a non-readable format. Now, these schemes, now we are trying to analyze how you can break them. So CSE-Cyber can be broken when you understand that the shift is 3, right? But when it comes to AES, to break it, you will have to understand this key that is going in. See that? So to understand the key, like standard AES is like almost like 128-bit key. So it comes to the complexity of like understanding the key that we have used. It comes to 2 raised to 128-bit searching. Okay, so you'll have to search among that possible key values, and then you have to try all the possibilities, and then you have to decrypt it. So that's actually very complex. Like, so that's where AES is very good scheme. Just to give you a glimpse of why it is like the best algorithm that is there. Okay. Now, when it comes to asymmetric schemes, it is based on mathematical principles. So here you can see that the ciphertext is generated using m raised to e mod n. Okay, so it is based on the fundamental that m raised to two values, that is e and d, product of e and d, mod n is going to be m itself. Okay, so I'll just okay. Yeah. So it's based on the concept that m raised to two values and mod n, okay, is going to be m itself. Okay. So what you have is actually a combination of two values, e and d. Okay. Now, when you actually raise m with e and you do modularity over n, you get a value. Okay. Now, when you apply, you know the d value, and then you on to the resultant when you apply, like let's say it works. So m raised to e mod n is actually x. Okay. Now, x raised to d is going to be what? You will get back m. Clear? So it's based on mathematical combination. Like you create a pair called e and d, and you do operation with one of them, and you get a resultant. And only if you know the secret that you have kept aside, like the pair associated with it, you can get the m. Okay. So I hope it is clear that it's based on some mathematical complexity. Like earlier, it was certain operations, but now it comes to certain mathematical complexity. Like, so what is that complexity is? So here, if you see this value, how this E and N is generated. Okay. So how you generate E and N is like you start with two values, P and Q. Okay. Then you have calculate n from that. Then you have a phi of n. I'm not getting into the details. Like phi of n is going to be like the set number of co-primes of n. So it's always going to be p minus 1 and q minus 1 into q minus 1. So you have the value phi of n. Now you calculate e using GCD of phi of n comma e is equal to 1. So you fix a value e such that GCD of phi of n and e is going to be 1. Okay, so why we are doing this is because only if these E and D satisfy these properties, we will achieve that. M raised to ED mod n is equal to M, that property. Okay. Now, based on the E we have selected, we calculate the D. Okay, clear? So the concept is that D known, you have the phi of n, it is very easy to calculate D given E. Okay, clear? If you know phi of n, okay, it is very, and given you have E and N, it is very easy to calculate D. Okay. So if you don't know phi of n, it's very difficult to calculate D. That's the private component usually. Okay. Now to find this phi of n, you need to factorize this n. Okay. You need to factorize P and Q. Why? Because phi of n is p minus 1 into q minus 1. Okay. Now, RSA was very good. It was very giving us good security. Why? Because there is no classical algorithms which can find P and Q in polynomial time. See, if I'll ask you what is the factors of 15, you can easily find, tell me that it is 3 into 5, right? But when it comes to very large n, it's very difficult to find that. Okay, so RSA was based on that complexity. Okay, so it was very difficult to find phi of n, or basically find P and Q. Okay, so we were good with this. Now, suddenly what happened is, so this is actually an example where it works like 2 raised to 5 mod 4, and you have 4, and 4 raised to 11 mod 14, you get the 2 back. Okay, clear till now? Now, this is RSA, and these schemes have the problem that this is very complex in calculation. So usually what we do is we use the combination. We use symmetric schemes for sending the data, okay, in secure form. Like we use a key to encrypt them, right? So for sending the keys, we use asymmetric schemes. Clear? So that's how we used to currently it used to exist that way, and we were good. And I'm also introducing hash schemes to you. I believe hash is already introduced in the first session itself. So hashes are certain algorithms which acts like a one-way function. They have certain properties that I have listed here. We have one-way property, weak collision resistance, and strong collision resistance. Now, what I want to emphasize here is how hash functions are constructed. It's again constructed based on operations. Okay, it's not mathematical complexity. Like it's not based on some mathematical hardness of a function. Okay, that's what like complexity is related on the operations, but like the hardness of breaking a hash function is equivalent to reversing the operations that we have done. Okay. So that also is like how hash functions is built. So hope it is very clear. Symmetric schemes are dependent on certain operations. Asymmetric is based on some mathematical hardness. And hash is again certainly based on operations. Okay. Now, suddenly, like why people are discussing about these issues. So for that, we have to understand what is quantum computing and what advantage it gives to the system. Like we understood how to break these systems, right? So why quantum computing is going to break these systems is first thing what we have to analyze. So under quantum computing, so you can see that I have like given a comparison. It's like sort of self-explanatory. You have in classical, you have like ones and zeros, whereas in quantum computing, you have vectors. Okay. And there is exponential proportion like in the qubits, like suppose you have 5 qubits, you can represent 2 raised to 5 values in one go. Okay. And obviously, like classical computers are sort of established by now. We have low error rates in the computation unless and until we go for atomic scale stuffs currently. Like as per Moore's law, when the size is decreasing, there is like we see that there is certain errors. Why? Because there is like classical physics is not able to explain the properties at these very nano scale, like very minimal scale, at the subatomic scale of elements. Like we have reduced the size of these transistors so much that it all comes down to the size of like these molecules. Okay. So when that comes in, the classical physics won't be sufficient to explain the properties or the issues that we come across. So comparing with classical computing, like quantum computing currently is like highly error prone. In the future, obviously, we'll have error correction schemes and all. Currently, we have like classical systems, which is highly stable, right? We don't see fluctuations or bit flips and all. Earlier days, we used to see that. But currently, we don't see issues of bit flips and all. There were situations in certain CPUs and all, but it's like sort of stable, right? So when it comes to quantum computing, like how you define a certain state is using this notation. You have like values of zeros and one. It's based on probability assurance. I mean, probability calculations. So I'll explain very simple terms. Like you have you have a state, okay? Now you want to know whether the state is going to be in 0 or 1, right? Now, how to measure that state is dependent on the probability associated with it. So if the alpha value is going to be maximal, okay, so here you have seen that alpha raised to square, beta square is always going to be 1. So it balances out. So if the alpha is going to be maximum, like 1, then always we are going to get the output as 0. Now, if beta is going to be 1, we will get the output as 1. Now, if the alpha beta variance probability is like varying, there is chances that we will get certain, I mean, unpredictable. If it is equivalent, there will be chances that we can get random outputs also. Okay. So at this phase, like what I want you to do is like, I want you to go to the quantum computing link, the account you created. Like I want you to explore at least one simple program. Now, before that, I want you to like in the important links, there is something like Rigetti's link is there. So to make you understand how the quantum architecture is structured, like they have a very good representation. So you can use that link and you can click on these like these shell. So this is how a quantum processor currently looks like. It has to be cooled down. I mean, it's Rigetti system. There are other architectures, physical architectures as well. So for Rigetti, this is the architecture that is followed. So you have the like the second phase is the machine or the nerves. And then you have the heart. And then you have the skeleton and you have the brain where the actual processor sits, to help you visualize like how it currently looks like. Now, you can search for current quantum computing machines. It's like the earlier vacuum tubes systems, like it is filled in a room and you are in that state. Like the entire room is like related to, I mean, the configurations are spread across the room, which is equivalent to the olden days of having the vacuum tube based systems. Now you can go to the IBM Quantum. Like I want you to launch the composer. So in IBM Quantum, there is like two areas where you can like play across and try to explore this area. One is the composer and you can have the lab. So in the lab, you can have like write the code from the scratch, like you can create the circuits and push it for actual quantum computers, etc. And in Composer, it's like a beginner friendly area where you get an experience of the different gates and the structures that is there. So in Qiskit, it's default to 0. Okay, so the quantum state is default to 0. Okay, so here you can see that this is the measurement symbol. Okay, so I will explain what is measurement, etc. and all, and like phenomenons which is coming. So this is the measurement symbol, and you have the certain gates, like you can even define custom gates as well. And so here, as you can see, it's defaulted to 0. And if you want to convert it into plus, so you can like use the gate and you can convert it into plus. So that's how like the simplest one. Now, very important phenomenon in quantum is actually superposition. So the H gate helps you to achieve that. So here you can see that the probability is actually equivalent for 0 and 1. Just play around with it. Okay. Are you guys doing, or we will continue? At least just try to see, or if you don't have a system, You can even see a generic, a simple quantum circuit online. Just simply search for quantum circuits and like how it works and all. I'll give you 2 minutes. So it's 25, we'll resume at 27. Okay. Now also in the link, important links, there is one thing like QSkit textbook. So in that you have a link there for the first link, which actually helps you to understand all the basics in that. It's very interactive textbook by QSkit. You can learn all the gates and phase things and all there. And also there is another link called Qubit. Here I have put like to understand the block sphere. So I'm not getting into the details. There is like the block sphere is the representation of the state. So like you can understand how the angle and the phase affects the final, what should I say, like the measurement outcome. So you can like learn about that and all using this link. So it gives us step-by-step explanation also, like you can go through that. Okay. Now, suddenly, like, what is the impact? So what happened is quantum computing is not something which is very new. It's like there from like Max Planck's Albert Einstein era and all. But the thing is that quantum computing or these technologies where, it's used in many of the applications devices, like even let it be microwave, or there are a lot of things where applications are there. But when it comes to computing, like where you have to manipulate data and you have to do certain operations, for that you need to encode information into this. So for understanding the difficulty there, I want to emphasize on the fact that quantum computing is based on elements at the subatomic scale. Okay, so it's not physical based physics. Like quantum physics is based on elements at the subatomic molecular scale, right? So these elements have certain properties. Okay, so these properties is what like helps in achieving certain advantages. Like we have superposition, which we will see in the next slides. So there are certain phenomenons in these quantum, or there are certain quantum phenomenons which we can make utilization of for advanced computations, building advanced crypto systems, etc. Right now, we were very good with RSA, right? Why? Because there was no classical algorithm which can factorize n. Okay. Now, what happened is Peter Shor, he developed an algorithm called Shor's algorithm, which can effectively factorize numbers in polynomial time. See, it's a good thing. We can solve a lot of problems associated with factor, which, it's giving you some advantage. We can factorize very big numbers in a polynomial time. But what happened is it had a negative impact in classical crypto systems. So our asymmetric key crypto systems are completely affected by that. We also have Grover search, which is actually like the current best possible search on like unsorted data. We know the complexity is big of n, right? See, you have 10 values. You need to see it's unsorted, or you don't know any details about the values in the set. Okay. Now, if you need to find if a certain value is there in the set, you have to search and entire set, right? So the complexity is big of n. Now, what happened is Grover's search reduced this complexity to big of root n. Utilizing a certain quantum phenomenon, we could accelerate that. So what it does is it shifts the phase of the value that we are looking for, and it amplifies the amplitude of that particular value. Like if you represent 0, 0, 0, like you had the graph, no? So what we'll do, suppose we have like 0 to 7, and I want to search 5. Okay. So I'll flip the value, phase of the 5, and whichever is like unflipped, I'll reduce the amplitude. Whichever is flipped, I'll increase the amplitude, right? So what happens is by the end, the value I'm going to search, its amplitude will be maximized. And when I measure, I'll get that value. So it has reduced the number of operations required to big of root n. So why I'm telling about these people, Grover's algorithm is, I told you like AES algorithm, right? So the difficulty in breaking AES is equivalent to searching the entire set, 2 raised to 128, right? So what happened is AES is not broken, but it has reduced to half of the security. Like if it was 128, it has reduced to 64-bit security. So we have to go with higher numbers. But hash and symmetric, we can still keep using the ones, but with higher bits. Whereas asymmetric schemes, we need the replacement. Okay. So this is the impact. This is like the slide from NIST. And we can see that the public key crypto systems is completely broken, and symmetric key we can continue using, whereas same with hash and key management systems, etc. Now, what do you know? What is the current qubits that is available? Okay, so if you go to this, like the currently used RSA is 2048. So to break that, you need a minimum of 4098 qubits. Now, do you know what is the current state of qubits that is available? Almost in the range of 400, 433, 450 range. So like 4098 is like far ahead, right? So it's very important question, like, should we actually worry about it now? Like, why can't we like keep increasing the RSA size? Like we were using 2048. Instead of using 2048, why can't we go for 4096 bits and continue using the systems, right? So what is the problem is there is related to complexity. So that's where we have like post-quantum crypto systems as well, which is already discussed. Like you had lattice, and you have a session on specifically post-quantum as well, which is coming. Now, along with that, we have quantum crypto. Okay. So to understand if you need to worry, there is actually a Moscas theorem. So what it states is that suppose our data is going to be having a long lifetime. For example, defense. It's a very important data system, right? Like we have the, like suppose, let's say there is a missile information or some building architecture or internal structure. Even our health information, right? So our health information is going to be valid for our lifetime. And we expect that quantum computers are going to come in within 10 years, like very usable, and RSA is expected to be broken by within 5 years, like 2025 is sort of predicted. And so the time to worry, like if your data is having a bigger lifetime, okay, and if it needs to be secured even after the quantum computers come into existence, then you have a problem. You need immediate shift. Okay. If it is like short-term data, which will be expired within certain times, then it's not a problem. You can continue using these schemes, but if the data lifetime is bigger or higher, then you need shift from the classical systems to quantum safe systems. Okay. So this is like the quantum phenomenon based. We have like solutions, and we have certain physical phenomenon based solutions as well. We have post quantum cryptography and combined architecture, and we will be focusing on quantum cryptography. Okay. Now, quantum cryptography, as explained here, exploits the naturally occurring properties of quantum mechanics. So, as I told, there are certain phenomena associated with these quantum objects. Okay, so we make utilization of these phenomena to construct cryptographic systems. So that is quantum cryptography. So hope it is clear. Post-quantum cryptography is still based on mathematical principles, whereas quantum cryptography is based on quantum phenomena. Okay. Now, the examples are quantum key distribution. So that's why I highlighted the importance of asymmetric key systems. Like we were using it for key distribution. So that's where QKDs play a very relevant role. We make use of quantum phenomena to establish key exchange. Okay. Then we have quantum secret sharing. We have quantum secure direct communication. We even have quantum random number generators, and we have quantum stream ciphers, etc. So these are like currently being studied, and a lot of schemes are there, but they have certain implementational constraints, which we will try to understand in the coming slides. So as you can see here, there are two approaches here. Quantum states can be made possible to improve cryptographic protocols, protecting the classical information. So what we use is, we will continue using AES for encryption, and the key associated with it will be shared using QKD. Okay, so we are still protecting classical information, right? Now, the second approach is like we will protect quantum information. Okay, so that is like quantum secret sharing, etc. So what you actually share is quantum information as the secret. It's not classical information. Okay. So now summing up everything that we discussed, like quantum phenomena, uses separate individual quantum objects. Now, what are these objects is molecules, atoms, electrons, and photons. So that is the fundamental difference there. Okay. Now, can you tell me, like, what do you think? Like, will quantum computers replace classical computers? What do you think on that? Yes. How many are telling yes? Okay. How many are telling no? No. So they will coexist. They'll never replace. So like what you have to understand is like, to help you understand, I'll give you an example. So candle and bulb, both are light sources, right? So candle has its own advantages. It has its own cons, right? Bulb also has its own advantages, and it has its own cons. Now, however you try to improve a candle, you'll never get a bulb out of it, right? And if you do anything on the bulb, you'll never get a candle out of it, right? So there are certain scenarios where candle is going to help you, like there is no power source. You don't need a bulb, right? You have a very good set of candles with you. You can go ahead and use that. And there will be situations where you don't have a area where you cannot, I mean, there is convenience things and all. So bulb is better, right? But candles is never going to replace, I mean, bulbs is never going to replace candles. They exist. Did they replace? No. So what you have to understand is, there is certain operations or problems that require quantum phenomena. Okay. That's when you need, you can make use of these technology. Like for example, to multiply two numbers, you really don't need these phenomena, superposition, entanglement, blah, blah, blah. You really don't need. But if you need to search an n set, which is very huge, like Grover's algorithm can be used to fasten the search, right? So depending upon the problem, you can like make use of these phenomenons or like technology. So maybe in the future, we'll have like CPUs that switch between these phenomenons, or like we'll have classical CPUs as well as quantum CPUs in that. And certain times they will make use of these quantum phenomenons for computation. Otherwise, it will, like we have cores and all, right? So definitely for watching a movie or like live streaming, you really don't need these quantum phenomenons, right? So they are never going to replace. There will be CPUs that is maybe going to switch between these phenomenons and utilization of these phenomenons. Okay. So to help you understand this phenomenons, I would like to go to a different slide. 1 second. So one of the very fundamental concept is like explained using Schrodinger cat. Okay, so like here the diagram that I got has both Poisson and radioactive objects. Like, so what it happens is you have kept a cat in a box with a radioactive object as well as a poison. Okay, so now what happens is like you have closed the box. Now, till the time you keep the box closed, you don't know whether the cat is dead or alive, right? So in the closed state, you call it in a superposition of dead and alive. Okay, so that's the concept of superposition. You don't have like an idea of what state the box is in. Okay, clear? So once you make an observation, what do you mean by an observation? You open the box, right? Then the state of the system collapses to either dead or alive. Okay. So the quantum state is that it is always going to remain in superposition. When you make an observation, it collapses to any of the state. Okay. So once you make an observation, you have interrupted the state of the system. Okay. Clear? So it's like you have made an observation, and it's like you have made a measurement of the state of the system. Okay, clear? So that's the importance of Schrodinger cat. Now, another like a very important principle is uncertainty principle, which is again like already covered. So you understood that until the box remains closed, you cannot predict the state of the system. So you have already learned about this in these experiments, right? Split experiment. So when the size of the split has gone to a very subatomic scale, you really cannot predict where the electrons are being incident. Remember? Physics. Yeah. So when the split was very big, you can clearly predict, because that falls into classical physics, right? You can clearly predict where it is. But when the split is very small, it falls under quantum physics, then uncertainty principle comes into picture. You really can't predict where the electrons are going to be incident on. Okay. Now, superposition, as we already know, like both states coexist. So here, the observation is what the eye does. Okay, so the state is fluctuating between 2, 0, and 1. So when we make an observation, it falls to either one of the states. So in this case, it is falling to 1. Okay, so that is superposition. Now, entanglement is something like we call it like telepathy. I mean, it's not clearly telepathy, but to make you guys understand, you can connect, I mean, relate it to that. So two systems, two people are so much connected that you cannot differentiate them at all. Okay, so you, I mean, anything on the one person will be affecting on the other person, and anything you do on the other person will affect the other person, two objects. So it is a composite system, but you cannot define the system using individual components. Okay, so you will have to define the system as a whole only. So that is entangled. So there is fully entangled photons, like you can create them in labs. Currently, there are a lot of studies going on in establishing these phenomena. So once you have entanglement established, you can go for teleportation. Like you can encode an information in the first qubit. It will immediately teleport to the next qubit. Okay. Next is like interference. So to help you understand interference, like you have a pond, which is very stable. You throw a stone at it. Okay. So you have a ripples that is formed, right? Now, if you throw another stone, which is very close to the initial ripple, you end up with a new pattern of ripples, right? But if you have thrown the stone somewhat farther, they will independently exist, right? So interference is that like when you have some thing that came across to it and you end up with a final pattern. So that is interference. So this is how you do quantum computation. We will be looking at certain final state, right? So what we do is we will start with a maybe usually superposition or something like that, certain state. We will apply interference using certain gates and all, and we will make sure that finally we end up with the state that we are looking for. Okay. So teleportation, I have already told, like if they are connected, you can send information. Then very, very important theorem is no cloning theorem. So what it explains is that you cannot copy a quantum object. Okay, so it was very difficult to understand initially. See, you will encode a quantum state to 1. Okay, so why can't you like make an observation and then encode the next quantum qubit to 1? It is like a copy, right? But the thing is that you have to understand it is going to be in superposition. You at that particular time, you made an observation of 1. It doesn't mean that it is exact copy, like if you encode another 1 to a different qubit. You can never copy that. There is proofs for that. Just like you cannot copy quantum states to behave exactly the same. Maybe you can entangle them, connect them, but you cannot copy. Okay. So there is no cloning theorem. You cannot, like, as soon as you make an observation, you disturb the system. Okay. So, and once you finish the observation, it again falls to superposition, right? So next time you make an observation, it will again fall to something else. So if you try to make a copy of the observation that you made, it is not sufficient that there will be copies, right? So that is no cloning theorem. Same, it is related with observer effect. So if you need to make a measurement, you need to make a disturbance in the system. You need to make an observation, and that makes the system to collapse into a certain state. And as soon as you finish the measurement, it goes back to superposition. Okay. Now, another important phenomenon is tunneling effect. So in classical phenomenons, we know that if there is a potential barrier, and if the energy state is like below that potential barrier, you will never expect some objects to be on the other side of the potential barrier, right? But whereas when it comes to quantum objects, there could be some unpredictability in seeing the objects in the other side. Like you can see objects in the other side of the barrier as well. That could be because there could be interference coming from the systems we don't know. I mean, there could, like, you can see that you expect the object to be on the other side alone, but there is certain interference that is happening, which can be visible at the other end of the barrier as well. That is tunneling. So these are the important phenomena that we have in quantum computing. Okay. So now what we are going to understand is how we build crypto systems based on these phenomena. Okay. So the first important crypto system that we discuss is we are going to discuss is quantum key distribution. Okay. So I hope you understood that it's not creating an encryption scheme. What you're going to achieve is there is Alice and Bob. Alice and Bob will end up with the same key at the end of the protocol. Okay. It's not encryption or anything. You distribute a key. Clear? Any doubts till now? Okay. So under QKD, like we have two types of classification. There are n number of classifications. I wanted to introduce two types today. So one is like based on decoding of quantum state, and the other is based on the architecture. Okay, so in decoding method, what we have is like discrete variable and continuous variable. So for helping you understand, discrete variable means you do encoding with 1 qubit at a time. Okay, so you have to encode certain information, right? So you will encode 1 or 0 or whatever. So you will encode 1 qubit at a time, that is discrete variable. Okay. Continuous variable, we make use of maybe photon counts as the reference. Like for example, if the photon count is above a threshold, then it represents 1. Okay. Or if it is we have different methods are there in continuous variable, you usually use a set of photons. Okay. So it has a continuous stream. Okay. It's not 1 qubit at a time. So in 1 qubit at a time, you will encode it either as the base of the photon, face of the photon, or the angle, something you do on the photon, and you encode the information. Okay, so it's 1 photon at a time in discrete variable. Continuous variable, you will have like maybe the count as the reference or something like that. Now, based on the architecture, you have prepare and measure, and you have measurement assisted. So prepare and measure means you encode the state, and then the recipient will measure that. Okay, so based on that measurement result, there will be some communication between these two parties, and they will like end up with a key. Okay. Entanglement base means you will have entanglement between the parties, and using the entanglement, the pairs you have, entangled pairs you have between Alice and Bob, you will distribute a key. Okay. So now we are going to see first QKD, that is BB84 protocol. So in BB84 protocol, this is a discrete variable QKD, okay, and it is a prepare and measure, okay, QKD. Now, what it has is, it has two channels. One is classical authenticated channel, and we have a quantum channel. So you can see that the classical authenticated channel has two arrows, like there is to and fro communication, whereas quantum channel is only on the one side. So you have the information being sent from the sender to the recipient only. Photons are being transmitted from the sender to the recipient. Okay. Now, attackers can read both the channels. Okay. So that is the concept here. Now, how we establish key distribution using BB84 protocol? Sorry. We have two methods of encoding, that is on the diagonal basis and the horizontal basis. Okay. So in the diagonal basis also, you can encode 0 and 1. And the horizontal basis also, we can encode 0 and 1. So here you can see that 0 is encoded as degree 0 using this representation, 1 using this representation. This is horizontal basis. Okay. Now you have 0 and 1 encoded in diagonal basis using 45 and 135. Okay. So now, it's like polarizers. So if you match it through the correct polarizer, you will get the reading correctly, right? So when you have like these values pass through a diagonal filter, you will get a correct value. And if these values are passed through a horizontal filter, you will get the correct value. And if they are passed through a diagonal filter, you will get random values. Okay. That means that you will get encoding correctly. The recipient will read the values correctly. Whereas if they accidentally selected the wrong filter, they will get a random value. Okay. Similarly, when there is diagonal encoding, we have to pass it through the diagonal filter. If we pass it accidentally through a horizontal filter, we'll again get random values. Okay, clear? So now, like this is the simplest representation for BB84 protocol. So Alice has these 4 possibilities of encoding the values. Okay. And Alice will randomly encode values in these diagonal and horizontal filters. I mean, horizontal encoding methods. Okay. And Bob, what he will do is he will receive these values. Okay. Now, Bob will assume, okay, Alice had did the first one in horizontal one. Okay. Now, Bob obtained some result, which is 0. Obviously, they'll obtain some result, which is going to be random, which is not correct. So here you can see that it was expected to be 1, but Bob obtained 0. Clear? Now, in the next one, it was encoded using horizontal basis and it was passed through horizontal filter correctly. So the value obtained is correct. Okay. Now, similarly, for every qubit that Alice had sent, Bob repeats this. Okay. So Bob will end up with some value. This is called the row key. Row key. Okay. Initial key. Now, here this is mismatch, right? Bob has to discard them. Even Alice has to discard them, right? Now, how it happens is we already had a classical authenticated channel, remember? So we had a quantum channel through which the photons were transferred. Now, through the classical authenticated channel, we will send these filters, choice of filters. Okay. Now, Alice, when she sees that Bob had used a horizontal filter, Bob will know that, okay, Alice will know that it could have gone wrong, right? So Alice will also discard it, inform Bob, discard the first one. Clear? Now, similarly, Alice will inform which all needs to be discarded. Okay. So the keys that we end up with after this process is called shifted key. Okay. So ideally, if there was no eavesdropper, they both should end up with the same key after this process. Okay. But there could be chances that, okay, now tell me, the filter was actually transferred through the authenticated channel, right? Now, can't an attacker actually predict the value? Because the photons were transmitted through the quantum channel, and even the base, the filter information, choice of filters were also announced. Alice is going to announce which one to keep. Bob will keep that. Alice will also, remove the ones which are not supposed to be kept. Eve is also going to get this information, right? So how do you, how can we ensure the safety there or security there? What is the reason behind telling that this system provides unconditional security? It's because even if we have the filter information, to make use of the filter, you need these photons. Can Eve get the photon copy? No, no cloning theorem. Okay. If at all Eve tries to read any of the qubits, that also will be affected. So QKD not only secures, it also detects the presence of an Eve. Okay. Any attempt by Eve to read a qubit, that will disturb the system. So that's why we don't stop at sifting. We go for error correction and privacy amplification, right? So suppose this particular qubit is actually correct. Eve made an observation or an measurement in between. So what happens is this will change. Okay. So this value is actually expected to be 0, but after shifting, we will have 1 there. Okay. So in privacy amplification phase, what we will do is we will send a subset of the key, or like there are n number of methods. We will send a hash value of the resulting key and we'll match it with what Alice has. Only if both the values are matching, we proceed. Okay. So that is the quantum transmission. We have the filtration, the rectification, secrecy enhancement, and finally we have the quantum shared key. Okay. So in your important links, I have a very good simulator. It's not here. I'll add it. Don't worry. So this gives you a visualization of like how it works. So you have fixed orientations. Then if it is matching, you send single particles. So you always end up with a key. Whereas if you have like a mismatched orientation, then you will never end up with a key. Everything will be like discarded. So the assurance is that at least 50% of the shifted key will be, the row key will be remaining after that. Because we randomly select the filters, we'll at least end up with 50% of the row keys. We had 100 bits in the row key. After shifting, we can end up with minimum of 50 bits. Okay. So there is something like you can do in the, so if you go to this link and you go to the QSKIT textbook, you can go to that second link. Okay. There they are showing a implementation. Okay. So I want you to try that, like how encoding is happening. So here it helps you to visualize. One second. So here if you'll go, the preparation is done in X basis. And if it is measured in the same basis, then we are going to get the same value. Okay. And see, if in between the everything in the circuit is same, in between there was a measurement by Eve. So it disturbed the system. So what happened is there is a random output that we have. Okay. So I want you guys to like go to this simulator and just try this, like this X basis, like you can use that tutorial and try to simulate it in the composer. So if it is in the same basis, like if you use the same basis for measurement, you get the same value as you encoded. Like you have encoded 0, then you get it. But if you accidentally choose the ACID basis, then you get a random value. Okay. Just go through that link. If you don't have a system, you can go through that link. I'll give you again 2 minutes. We are almost coming to the end. 1:07 we'll resume. Also, what you see in the Q-skit is actually the simulation. Okay. Sorry. So that's fine. So in actual implementation, it's not like this. Okay, you have physical devices. You will have photon sources, single photon sources. Then you will have encoding devices. You have measurement devices. Then you have the quantum channel. All this will be physical. Okay. So what you are seeing in the Q-skit is actually the simulation of that. Okay. Okay. You can continue reading that after this session as well. Now we will, I would like to introduce to you the one of the entanglement based QKD protocol as well. So it's very simple to understand. You have entangled pairs between Alice and Bob. Okay. So if you do a measurement in X basis, it is going to be the same values. Like you encode it in one value, then there is chance that you receive the same one in the other end. Whereas if you encode it in Z basis, you have the anti-correlated, like you expect you will get the opposite. Okay, so that's the only thing. That's the simplest one, which is E91. So you have two entangled qubits. So if you encode it in X basis, you whatever value you get it at Alice end, keep it as such. Like you made an observation at Alice end to be 1. Then Bob is also going to be having 1. The encoding is in X. Whereas if it is in Z, if Alice observes 1, then it means that Bob will have to, Bob's observation has to be flipped. Okay, so Bob is going to get 0. So to both parties to end up with the same key, they have to flip it. One of the parties have to flip it. Okay. So QKD, based on entanglement is dependent on how the amount of entanglement between these parties. So obviously in discrete variable, there is problems with single photon sources. Like when you expect 1 qubit at a time, the photon sources should also give you 1 photons only at a time. If the photon source is faulty, what can happen is it can emit 2 photons, right? And with encoding, that information will be encoded in both the photons. Now, if there are 2 photons, Eve can copy or make measurement on one of them. Okay. So in discrete variable QKDs, it's very important to have the single photon sources, error-free. Okay. And even the measurement devices should be error-free. Why? Because if the measurement is having like faulty measurements, then the 0 and 1 encoding will not be read properly, right? So measurement devices also have to be properly configured. It should be error-free. Now, when it comes to entanglement-based QKD systems, it is the systems should share maximal entanglement. So there are methods to actually like evaluate the entanglement between the systems. Okay, so what we have to ensure is that they are maximally entangled. Otherwise, what will happen is if there is some entanglement left between the two people, Eve can come in and entangle. Okay. So what will happen is any information encoded on the one of the qubit will be visible to Eve also. So these systems require that the qubits has to be maximally entangled. Okay. So there is like, I have listed like how we make use of, that is monogamy of entanglement. Like I'm not getting into the details, like maximally entangled state is equal to established key is secure as the third party will never have an information about it. If there is some entanglement left, that entanglement left behind can be identified by Eve, and he can come into the system and entangle himself. Right. So that's with entangled based systems. Now, why the current scenario? Like to have QKDs properly established, we obviously need, as you can understand, like when it comes to discrete variable, you have single photon at a time, right? So these photons will be affected by even the minimal fluctuations, like even very high intensity light can fluctuate them, right? Or even some errors or some interference that can happen in the channel can affect them. So having proper quantum channels is another requirement, equivalent to having the devices. Now, to establish these QKDs, even QSS, QSDC, etc., we need proper quantum networks. Okay, like when it comes to QKD, we just need a channel between the sender and recipient. But if it is distributed with a very high distance, like the distance between them is very high, then there could be things that you need to manage in the quantum network. So that is one area which is very challenging. So which you guys can take up and research on that and all. So how we can improve the range for establishing the quantum networks and all those stuffs. So to understand the complexity, I have just kept this diagram. So in classical networks, we have repeaters. It was very easy to establish the concept of repeaters, right? But in quantum, inherently, they have no cloning theorem. You cannot establish repeaters, right? That itself is a big challenge. So how do you actually extend the range of these networks to establish QKDs or these communications for long range is actually a very big open problem right now. And I have few links in this document where I have listed few of the QKD implementations in India. And recently, Department of Telecommunication has launched a quantum communication network in India, and they have openly called for ethical hackers to break the network. And for each break, they are offering 10 lakh. This happened very recently on 27th March. So interested people can go behind that. So yeah, so those links are there in that document. I did not cover QKD in other countries. Why? Because China is like far ahead. You can read about that. They already use it in practical implementations like financial transactions. They are already using QKD networks for exchange of keys. So now when it comes to QSDC and QSS, as I told, they use encoding of quantum information. I did not cover that because they are like currently more theoretical. Like practically, there are solutions based on QKDs right now. So if you are interested in this area, like there is companies like QNU Labs in India, there is Q Labs, Tagbit, RRI. RRI is actually a research organization, like which is led by Urvashi ma'am. So one of the links is related to their study as well. So you can get in touch with these people and build these systems. I mean, understand, contribute in this area. So yeah, with that, thank you. If there is any doubts, thank you. If there is any doubts, you can ask or even get in touch with me. You can find me on LinkedIn. Online participants, if you have any doubts, I don't know where. Okay, it will be there, right? Yeah. So if you have any doubts, it's open. You can explore quantum computing, since this session is focused on quantum crypto. That's why I just covered the impact of quantum computing on current crypto systems, which is very important to actually understand why we need these systems. So that's why I started from there. But quantum computing is very open, like you have optimization problems, you can work on n number of problems. So if you're interested in that, you can work in that area as well. Need not be quantum crypto. You can learn quantum computing and how you can improve certain problems, solutions and all. So you can explore that as well. Okay, thank you.
Thank you, ma'am, for this descriptive session and for sparing time from your busy schedule to be here today. I request Dr. Panchami to kindly present Ms. Mahima with a token of appreciation.